exchange of ideas, thoughts, and information is called communication. The different languages spoken around the world are the result of man's continuous efforts to improve communication with each other since prehistoric times. However, effective communication requires an understanding of a common language. Developments in technology have also played a major role in the development of communication, making the process quicker and more reliable. Some early means of communication included sending smoke signals, relaying messages through drummers, and using signaling flags. However, none of them could be used to communicate across very long distances. The first major breakthrough in communication technology was the invention of the telegraph by F.B. Morse and Sir Charles Wheatstone. The next major breakthrough in communication technology was the invention of the telephone by Alexander Graham Bell and Antonio Meucci. Jagdish Chandra Bose and Guglielmo Marconi demonstrated the use of wireless telegraphy in 1895, freeing us from the use of wires for communication. The year 1936 marked a major milestone in wide-area communication, with the first television broadcast aired by the BBC. The first intercontinental facsimile was transmitted in the year 1955, using an idea patented by Alexander Bain in 1843. Advanced Research Projects Agency Network, referred to as ARPANET, was developed by computer scientist J.C.R. Licklider for the U.S. Defense Department in 1968. This system allowed transfer of data from one computer to another across the east and west coasts of the United States. ARPANET, ARPANET, paved the way for today's Internet that received a major boost by the invention of the World Wide Web by Tim Berners-Lee in 1990. Technological advances are continuing, offering us many different systems of communication for use in our everyday life. Let us now identify the elements of a communication system. As stated earlier, communication is the exchange of information between a sender of information and the user of information. The transfer of information from sender to user takes place through a communication system. Every communication system has three essential elements called the transmitter, channel, and receiver. The locations of the transmitter and receiver depend on the locations of the sender and user of information respectively. The channel is the physical medium that connects the transmitter and the receiver. Now, let us see how a communication system works. The sender of information sends a message signal to the transmitter. This signal can be in the form of voice, a written message, or any other form of data. Non-electrical message signals such as voice and text are converted into a suitable form to be transmitted through the channel and fed into the transmitter. The transmitter sends the signal to the channel. A channel may be a network of cables and wires or wireless information pathways through satellites. The transmitted signal suffers from distortion or noise as it moves through the channel and reaches the receiver as the received signal. The receiver filters out the noise from the received signal and regenerates the original message signal as voice or text before passing it on to the user of information. From receiving a message signal from a sender of information to delivery of the message signal to the user of information, all aspects of communication are taken care of by the communication system. Depending on the number of receivers receiving the signal from a transmitter, there are two modes of communication. They are point-to-point and broadcast. Communication systems like telephone calls that involve transmitting signals from a transmitter to a single receiver are called point-to-point communication systems. Communication systems like radio and TV programs that involve transmitting signals from a transmitter to a large number of receivers are called broadcasts. We have already learned that a communication system helps transmission of information from the sender to the user of information. Let us now learn about some terms used to describe different devices and processes in a communication system. A person using a microphone and speaker to transmit his voice over a distance is an example of a communication system. The microphone receives the voice signal and prepares it for transmission through the wire. A device that receives the incoming signal and prepares it for transmission through a channel is called a transmitter. Thus, the microphone acts as a transmitter. The loudspeaker receives the signal from the wire and reproduces the voice. A device that receives the signal and reproduces the transmitted information in a recognizable form is called a receiver. Thus, the loudspeaker acts as a receiver. The message signal is in the form of voice and needs to be converted into a suitable form for transmission through the wire. This is done by a device called the transducer. At the transmitter, the sound energy of the message signal is converted into electrical energy by a transducer. The electrical energy of the received signal is converted back into sound energy at the receiver by another transducer. Thus, a transducer is a device that converts one form of energy or information into another form. In communication systems, transducers normally convert voice, text, images, and videos into electrical signals and vice versa. Information is transmitted through a communication system in the form of a signal. Any information converted into electrical form, suitable for transmission through a communication system, is called a signal. A signal can be of two types: an analog signal, like the one that helps you watch programs on TV, or a digital signal that helps you type on your computer screen using a keyboard. Analog signals are formed by continuous variation of a quantity like voltage or current with time. Each analog signal can be represented by a sine wave. Digital signals are formed by discrete, stepwise variation of a quantity like voltage or current with time. Digital signals are widely used in electronic gadgets such as computers, digital cameras, and mobile phones. Computers can only understand numbers. Digital signals in most electronic devices are based on the binary system that uses only two numbers, 0 and 1, to denote low and high values of voltage or current. Each 0 or 1 is called a binary bit. Combinations of these binary bits are used to represent all kinds of information in electronic systems. Each number, letter, or special character on a computer keyboard is represented by a unique code in the digital signal sent by the keyboard to the computer. Numbers in digital signals are often represented using the binary coded decimal system, commonly referred to as BCD. This system represents individual digits by unique combinations of 4 binary bits of zeros and ones. Numbers, letters, and special characters can all be represented using the American Standard Code for Information Interchange, popularly known as ASCII, ASCII. ASCII uses coding of letters and characters in terms of numbers that a computer can understand. While traveling through a channel, a signal is often distorted by unwanted signals coming from inside or outside a communication system. Any unwanted signal that distorts a transmitted signal and disturbs its proper transmission through a channel is called noise. Signals are transmitted as waves, and their strength depends on their amplitude. Signals lose their strength during transmission through a medium. This loss of strength of signal while propagating through a medium is called attenuation. To compensate the loss of strength of the signal while propagation, the amplitude of a signal is increased wherever required during transmission. This process is called amplification. The strength of the signal increases during amplification. A device used for amplification of a signal is called an amplifier. A signal from a device corresponds to a specific range of frequencies in the entire spectrum of waves. The frequency range, or portion of the spectrum along which a signal travels, is called its bandwidth. The largest distance from the transmitter at which a signal can be received with sufficient strength is called the range of the signal. Low-frequency signals have a shorter range as compared to high-frequency waves. To increase the range of a low-frequency signal, the transmitter superimposes the low-frequency message signal on a high-frequency carrier wave. This process is called modulation. When a modulated wave reaches a receiver, the low-frequency message signal is retrieved from the high-frequency carrier wave. This process is called demodulation. Amplification and modulation can increase the range of a signal only to a limited extent. To further increase the range of a signal, we use devices called repeaters. A repeater is a combination of a receiver, an amplifier, and a transmitter. A repeater receives signal from a transmitter or another repeater, amplifies it, and transmits to another receiver, at times with a changed modulation. Using multiple repeaters, the range of a signal can be increased to a very large extent. Communication satellites in space are examples of repeaters. You have learnt earlier that a transfer of a message signal onto a carrier wave by varying the amplitude of the carrier wave is called amplitude modulation. The message signal used to modulate the carrier wave is also called the modulating signal. You have also learnt earlier that the expression of a sinusoidal message signal is given by the equation mt is equal to am sin omega mt, where am is the amplitude of the signal and omega m is its angular frequency. Let this be equation 1. The equation for a sinusoidal carrier wave is given by the equation ct is equal to ac sin omega ct, where ac is the amplitude of the carrier wave and omega c is its angular frequency. Let this be equation 2. The equation for the amplitude modulated wave is given by the equation cmt is equal to ac sin omega ct plus mu ac sin omega ct into sin omega mt, where mu is the modulation index of the modulated wave, which is the ratio of am to ac. Let this be equation 3. This equation is further modified to get the equation cmt is equal to ac sin omega ct plus half of mu ac into cos of omega c minus omega m into t minus half of mu ac into cos of omega c plus omega m into t, which you have learnt earlier. Let this be equation 4. Production of amplitude modulated waves, referred to as AM waves in short, is a multi-step process. Let us learn about the various steps involved in the production of AM waves. Amplitude modulation can be done by various methods. Here is the block diagram of a conceptually simple method. The block diagram shown contains an addition device, a square law device, and a band pass filter centered at omega c. The first step in the production of amplitude waves is the addition of the modulated signal to the carrier wave. The output of this process is a function x of t. Thus, it is given by the equation am sin omega mt plus ac sin omega ct. Let this be equation 5. Comparing equation 5 with equation 4, we find that sinusoidal waves with the upper and lower side frequencies are missing in the output of the addition device. These waves are generated by the square law device. The output of the addition device is passed through a nonlinear square wave device, whose output y of t is as given by equation 6, where b and c are constants. Substituting the value of x of t from equation 5 in equation 6 and simplifying, we get equation 7. Applying the trigonometric relation, sin square theta is equal to 1 minus cos 2 theta by 2 to the sine square terms in equation 7, and simplifying, we get equation 8. Applying the trigonometric relation, sin alpha into sin beta is equal to 1 upon 2 into cos alpha minus beta minus cos alpha plus beta to equation 8, and simplifying, we get equation 9. Comparing the output of the square law device given by equation 9 with the amplitude modulated signal given by equation 4, we find that equation 9 contains several terms in addition to the terms of the form found in equation 4. The addition terms in equation 9 include a non-sinusoidal term as shown. Terms that do not include a sine wave factor are called DC terms. In addition to a DC term, equation 9 also contains sinusoidal waves corresponding to the modulating signal, and the harmonics of the modulating signal and of the carrier wave. The output from the square law device is passed through a device called a band pass filter that allows only a specific range of frequencies to pass through it. The band pass filter removes the DC term and sinusoidal waves corresponding to the modulating signal and the harmonics of the modulating signal and of the carrier wave from the output of the square law device. The output of the band pass filter is given by equation 10, that is, of the form as in equation 4. Thus, the output of the band pass filter is an amplitude modulated signal. The amplitude modulated signal is then passed through a power amplifier that provides it the necessary power to account for attenuation and satisfactory transmission over a desired range. The power amplified amplitude modulated signal is then transmitted using an antenna of appropriate size depending on the wavelength of the AM signal. Now let us discuss the detection of amplitude modulated waves that involves receiving of the AM signal by a receiver and demodulation of the AM signal to reconstruct the original modulating signal. The AM signals received by the receiving antenna are passed through an amplifier to make up for attenuation during transmission. The amplified received signal passes through an intermediate frequency stage, where the frequency of the carrier wave is lowered to aid better detection of the modulating signal. After passing through the intermediate frequency stage, the AM signal is fed into a detector that separates the modulating signal from the carrier wave. A detector consists of two sub-devices called the rectifier and the envelope detector. The rectifier converts the AM wave into a rectified wave as shown. The envelope of the rectified wave represents the modulating signal. Thus, the rectified wave is passed through an envelope detector that demodulates the rectified AM wave to recover the modulating signal or the message signal. The recovered message signal is amplified and fed into a suitable device to produce the desired output. Here, it is observed that the waveform changes several times during the process of detection of the amplitude modulated waves. We have learnt earlier that communication systems are used to transmit both analog signals as well as digital signals. Analog message signals are transmitted over long distances as electromagnetic waves. The electromagnetic spectrum acts as the mode of transfer for information. The information contained in a message signal may be voice, text, images, videos, or some other form of data. Different kinds of information are transmitted using message signals of different ranges of frequencies. The electromagnetic spectrum is divided into different ranges of frequencies to transmit different kinds of message signals. Each of these ranges of frequencies is called a frequency band. Each frequency band has a lowest and a highest frequency used to transmit a particular kind of signal. The difference between the highest and lowest frequencies in a frequency band used to transmit a message signal is called the bandwidth of the signal. For example, telephonic voice signals are transmitted using the frequency band from 300 Hz to 3100 Hz. Thus, the bandwidth used to transmit telephonic voice signals is 3100 Hz minus 300 Hz or 2800 Hz. Note that 2800 Hz does not refer to the particular frequency used to transmit voice signals in telephonic communication systems. It rather refers to the range from the lowest to the highest frequency in the frequency band that is used to transmit the voice signals. Electromagnetic waves are also used to transmit digital signals over long distances. The rectangular waveform of a digital signal is actually made of a large number of sinusoidal waves superimposed over each other. Thus, for transmission, a digital signal must be decomposed into a set of sinusoidal waves at the transmitter. The same sinusoidal waves are then superimposed onto each other for reconstruction of the digital signal at the receiver. A digital signal can be decomposed into a fundamental sine wave with frequency nu0. That is, the reciprocal of the time period t0 of the digital signal. Besides the fundamental wave, the digital signal is made of an infinite number of other sinusoidal waves called higher harmonics with frequencies equal to integral multiples of the fundamental wave frequency nu0. The sum of all these harmonics with the fundamental sine wave are required for distortion-free transmission and reconstruction of the digital signal. Transmission of the fundamental sine wave corresponding to a digital signal with its infinite number of harmonics will require infinite bandwidth. However, it has been observed that higher harmonics make very little contribution to transmission and reconstruction of a digital signal. Thus, bandwidths for digital signals are chosen to include just a few harmonics that are sufficient for satisfactory reconstruction of the digital signal at the receiver. Message signals in communication systems travel through different kinds of channels that support different bandwidths. Coaxial cables that are widely used in internet connections and cable television networks offer a bandwidth of 750 MHz. Optical fiber cables that have revolutionized communication systems worldwide offer a phenomenal bandwidth of over 100 GHz. Optical communication using fiber is performed in the frequency range of 1 THz to 1000 THz. Satellite communication systems use radio waves traveling through free space as a communication channel. Radio communication offers a wide range of bandwidths for important commercial communication systems as shown in the table here. The allocation of bandwidths for radio communication is done as per international agreements and the International Telecommunication Union. We have learnt that analog and digital message signals in communication systems are transmitted over long distance in the form of electromagnetic waves. Depending on its frequency, a signal may propagate in the form of ground waves, sky waves, or space waves. Let us learn more about these different ways of signal propagation. We know that the product of the frequency and wavelength of an electromagnetic wave is constant and is equal to the velocity of light, which is a constant and is equal to 3 × 10⁸ meter per second. As the frequency of an electromagnetic wave decreases, its wavelength increases. Thus, low-frequency signals have large wavelengths. For example, consider a signal with a frequency of 3 MHz. Then, the signal has a wavelength of 100 meter. The wavelength of the signal plays an important role in the size of the transmitting antennas. To have an efficient transmission of signals, the size of the transmitting antenna should be nearly equal to at least 1/4 of the wavelength of the signal that it needs to transmit. Thus, larger the wavelength of the signal, larger is the size of the transmitting antenna. Thus, in the example considered, the size of the antenna should at least be 25 meter. Antennas of such large sizes are located on the ground, usually as tall transmission towers. Such transmission towers are used to transmit signals with low frequencies up to a few megahertz only as surface waves or ground waves. A signal propagating as a ground wave travels along the surface of the earth. A propagating ground wave induces current over the ground on which it travels. This leads to a loss in signal strength or attenuation. Even a slight increase in the frequency of the signal results in large-scale increase in the attenuation of ground waves. Thus, ground waves are used to transmit low-frequency signals only. The range of a ground wave depends on the frequency of the signal and the power radiated by the transmitting antenna. Amplitude-modulated radio broadcast signals propagate as ground waves. Signals with frequencies ranging from a few megahertz up to 30 megahertz propagate as sky waves. Signals traveling as sky waves from a transmitter are reflected back to a receiver from a layer of our atmosphere called the ionosphere. Ionosphere is formed due to ionization of air molecules by ultraviolet radiation coming from the sun. This layer extends from around 65 kilometers to 400 kilometers above the Earth. The degree of ionization varies with the height from the surface of the Earth. The density of atmosphere is not constant. It decreases with height from the surface of the Earth. At greater heights, the solar radiation that causes ionization is intense. But as the density of atmosphere is less, the degree of ionization is less. At lower heights, the density of atmosphere is comparatively larger, but the intensity of solar radiation is comparatively less. Thus, again the degree of ionization is less. However, at some intermediate heights, the density of atmosphere and the intensity of solar radiation are comparable to have a high degree of ionization. Depending on the level of ionization, the ionosphere is divided into 4 layers, as shown. Different layers of the ionosphere help in the propagation of sky waves of different ranges of frequencies, as shown in the table. Short-wave radio broadcast signals propagate as sky waves. Signal waves with frequencies greater than 30 MHz can penetrate the ionosphere and do not get reflected by it. Thus, signal waves with frequencies greater than 30 MHz propagate as space waves. Space waves travel in straight lines. Thus, the transmitter and receiver of space waves must be visible to each other without any obstruction in between. This is called the line of sight communication. In the line of sight communication, a transmitter and a receiver can be in line of sight only if they are at or above the horizon of each other. If we know the height ht of a transmitting antenna, we can find the distance dt to the horizon from the antenna. Let us understand how to find dt. Consider a point P on the horizon, to which we need to find dt. Let the point at the height of the antenna be Q and the center of the earth be O. Then, the triangle formed by joining the points P, Q and O is a right-angled triangle with right angle at P. Using Pythagorean theorem, we get OP square plus PQ square is equal to OQ square. This gives R square plus DT square is equal to R plus HT square. On simplifying, we get DT square is equal to 2RHT plus HT square. As HT is much less than R, we neglect the term HT square in the expression. This gives us the distance dt of the horizon from an antenna of height ht is equal to under root 2 RHT, where R is the radius of the earth. Similarly, the distance dr of the horizon from a receiver of height hr is equal to the under root 2 RHR. The maximum distance d for line of sight communication between two antennas with heights ht and hr is given by the sum of their distances from the horizon as shown here. Thus, line of sight communication is possible over a greater distance by increasing the heights of the transmitting and receiving antennas. Due to curvature of the earth, it is not always possible for a pair of transmitting and receiving antennas to be in line of sight. In case if a pair of transmitting and receiving antennas are not in the line of sight, they can still communicate using space waves through a communication satellite. Thus, space waves are also used in satellite communication. Television broadcast signals propagate as space waves. We have learnt earlier that modulation is the process of superimposing a low-frequency message signal onto a high-frequency carrier wave. Let us now know more about the process. Long-distance transmission of signals is done using electromagnetic waves. We know that the product of the frequency nu and the wavelength lambda of an electromagnetic wave is constant and equal to the velocity of light c, which is 3 × 10⁸ meter per second. Now suppose we need to transmit a message signal of frequency 25 kHz. Submitting the value of this frequency in the expression and simplifying, we get the wavelength of the message signal equal to 12,000 meter or 12 kilometer. For proper transmission of a signal, the size of the transmitting antenna must be comparable to the wavelength of the signal. Its length must at least be of the range equal to 1/4 of the wavelength of the message signal. Thus, to transmit the 25 kHz message signal, we require an antenna that is at least around 3 km or to the maximum of 12 km wide. This is quite impractical. In order to use an antenna of a smaller size, we need to reduce the wavelength of the message signal. One way of reducing the wavelength of the message signal is to increase its frequency. As the velocity of the wave is constant, an increase in the frequency of the wave results in a decrease in its wavelength. But the original message signals are confined to low-frequency base bands. This requires transformation of the low-frequency baseband message signals to a high-range radio frequency before they are transmitted. If we transform the low-frequency message signal of 25 kHz to a high-frequency radio signal of 25 MHz, the wavelength of the signal to be transmitted reduces to 12 meter as per the calculation shown. As the wavelength reduces to 12 meter, the size of the antenna required for transmission of the message signal is reduced. Thus, the modulated wave can now be easily transmitted using an antenna of the size of about 12 meter, which is quite practical to build and operate. Hence, transformation of message signals is required to work with antennas of practical sizes. The quality of transmission of the message signals depends on the power radiated by the transmitter and repeater antennas. It is theoretically proved that the power radiated by a linear antenna of a given length is inversely proportional to the square of the wavelength of the signal. Hence, for an antenna of a given length, the power radiated from the antenna increases with the decrease in the wavelength of the message signal. We know that in order to decrease the wavelength of a message signal, its frequency must be increased. If the message signal is transmitted without increasing its baseband frequency, the power radiated from the antenna of a given length is very less. Hence, the frequency of the message signal should be increased from its baseband range to a high-range radio frequency before it is transmitted. Thus, the transformation of the baseband message signals to high-frequency radio wave helps to increase the power radiated by the antennas for better transmission of the signal. Message signals of the same frequency may be generated from different sources. For example, radio jockeys from different radio stations may generate voice signals of the same wavelength. If several message signals of the same wavelength are transmitted together, the signals may all get mixed up. This mix-up of signals can be avoided by using communication at high frequencies and allotting a band of high frequencies to each message signal to be transmitted. This gives rise to the need of translating low-frequency baseband signals to high frequencies such that the translated signal of high frequency possesses the same message that is contained in the original signal. In the process of translating the low-frequency signals to a higher level, we use the high-frequency waves called carrier waves. The process of attaching the information in the message signal to a carrier wave is called modulation. The high-frequency carrier waves used for modulation may either be analog sinusoidal waves or digital rectangular waves called pulses. The signal strength of a sinusoidal carrier wave is given by the equation Ct is equal to AC sine omega CT plus phi, where CT is the signal strength expressed in terms of current or voltage. AC is the amplitude of the carrier wave. Omega CT is the angular frequency of the carrier wave and phi is its initial phase. The equation shows that the signal strength of a sinusoidal carrier wave depends on its amplitude, angular frequency, and initial phase. In the process of modulation, any of these parameters, namely amplitude, angular frequency, and initial phase, can be controlled by the message signal, resulting in three types of modulation. They are amplitude modulation, referred to as AM in general, frequency modulation or FM, and phase modulation or PM. The transfer of message signal onto the carrier wave by varying the amplitude of the carrier wave in accordance with the amplitude of the message signal is called amplitude modulation. The transfer of message signal onto the carrier wave by varying the frequency of the carrier wave in accordance with the frequency of the message signal is called frequency modulation. The transfer of message signal onto the carrier wave by varying the phase of the carrier wave in accordance with the phase of the message signal is called phase modulation. The signal strength of a digital carrier wave or pulse depends on the pulse amplitude, pulse duration, and pulse position in terms of pulse rise or fall. Thus, the different types of modulations possible using a pulse carrier wave are pulse amplitude modulation or PAM, pulse duration modulation or PDM, and pulse position modulation or PPM. Pulse duration is also called pulse width. Thus, pulse duration modulation is also called pulse width modulation or PWM. Another type of modulation that is possible is the pulse frequency modulation or PFM, which is analogous to pulse width modulation. We already know that the transfer of a message signal onto a carrier wave by varying the amplitude of the carrier wave in accordance with the amplitude of the message signal is called amplitude modulation. Let us consider the case where the message signal, carrier wave, and the amplitude modulated wave are all sinusoidal waves. A sinusoidal wave, in its simplest form, is represented by a function of time yt equal to a sine omega t. Here, a is the amplitude of the wave and omega is its angular frequency. Let the message signal having amplitude am and angular frequency omega m be represented by the equation mt is equal to am sine omega mt as shown. Let this be equation 1. Similarly, let the carrier wave having amplitude AC and angular frequency omega c be represented by the equation Ct is equal to AC sine omega Ct as shown. Let this be equation 2. Then, the expression for amplitude modulated signal is represented by the equation Cmt is equal to AC plus am sine omega mt into sine omega ct. Let this be equation 3. The terms in equation 3 can be rearranged to get equation 4. In equation 4, the ratio am to AC, which is the ratio of the amplitude of the message signal to that of the carrier wave, is called the modulation index. represented by the Greek alphabet mu. To avoid distortion of the message signal during transmission, the modulation index must be less than or equal to 1. This implies that the amplitude of the carrier wave must always be greater than or equal to the amplitude of the message signal. On further simplifying equation 4, for the modulated signal, we get CMT is equal to AC sin omega CT plus mu AC sin omega CT into sin omega MT. Let this be equation 5. The expression sin omega CT into sin omega MT in equation 5 can be rewritten as half cos omega C minus omega MT minus cos omega C plus omega MT. Let this be equation 6. Here we use the identity sin x into sin y is equal to half cos x minus y minus cos x plus y from trigonometric transformations. Substituting the value of sin omega CT into sin omega MT from equation 6 in equation 5 and simplifying, we get equation 7. The difference between the angular frequencies of the carrier wave and the message signal in equation 7 is called the lower side frequency of the modulated signal. The sum of the angular frequencies of the carrier wave and the message signal in equation 7 is called the upper side frequency of the modulated signal. Thus, the amplitude modulated signal consists of a carrier wave with frequency omega c and two sinusoidal waves with frequencies equal to the lower and upper side frequencies. The lower and upper side frequencies form the side bands of the transmission spectrum of the amplitude modulated signal. The range of frequencies between the side bands of an amplitude modulated signal defines the bandwidth required for transmission of the signal. Amplitude modulation is used for broadcasting programs by many radio stations. Different radio stations use carrier waves of different frequencies so that their side bands do not overlap. This is essential for proper transmission of signals without interference with each other.